Welcome to this video on the effects of unbalanced currents in electrical circuits. Unbalanced currents in polyphase systems are unequal in magnitude or not properly phased, which can lead to significant consequences. The primary causes of current imbalance include uneven load distribution, single-phase loads on a three-phase system, and electrical fault conditions. Other causes are unbalanced supply voltage, defective equipment, and harmonic currents from nonlinear loads. Unbalanced currents immediately impact transformers. Effects include increased heating, reduced efficiency, premature insulation degradation, and localized hotspots. You may also notice increased audible humming or vibration. For electric motors, unbalanced currents cause unbalanced magnetic fields, leading to vibration. This results in reduced torque and performance, increased temperature rise, and bearing damage from wear, ultimately shortening the motor's lifespan. Cables and conductors also suffer immediate effects, such as overheating in conductors carrying higher current. This can cause voltage drop variations, potential for insulation breakdown, and a reduction in the system's current carrying capacity. This image summarizes the effects, showing consequences like overheating, reduced efficiency, voltage distortion, and motor performance issues. The imbalance also leads to malfunctioning protectors and system instability. System-wide, current imbalance causes power quality issues. These include voltage imbalance at load terminals and increased neutral current in four-wire systems. Further consequences are harmonic distortion amplification and a poor power factor. The economic impact includes increased energy losses due to I²R losses and reduced equipment life by 30 to 50%. Maintenance costs increase from repairs, and system capacity is effectively reduced, potentially leading to power factor penalties. Protection systems face challenges, including false tripping of protective devices and underprotection of overloaded phases. This imbalance also complicates device coordination and causes nuisance alarms from monitoring systems. Mitigation strategies for load balancing include redistributing single-phase loads and installing phase balancing transformers, such as Scott-T or LeBlanc. Using automatic load transfer switches and implementing load scheduling also helps prevent simultaneous high loads. Power conditioning solutions help mitigate current imbalance. These include static VAR compensators, active power filters for harmonic mitigation, and uninterruptible power supplies with balancing capability. Phase balancing reactors are another effective solution. Effective monitoring and maintenance are crucial mitigation strategies. This involves regular current measurements, installing permanent monitoring systems with alarms, and using thermal imaging to detect hotspots. Preventative maintenance schedules should be based on imbalance severity. Safety implications include fire hazards. Overheated conductors can ignite surrounding materials, leading to transformer explosions from excessive heating. Insulation breakdown can also result in dangerous short circuits. The risks of equipment failure are high. This includes catastrophic motor failure from bearing or winding damage and transformer insulation breakdown. Circuit breaker failure is also a risk due to persistent overcurrent. Current imbalance poses personnel safety risks, such as increased arc flash risk from equipment failure. Electrical shock hazards are present due to damaged insulation, and there is a risk of burn injuries from contacting overheated equipment. Detection and diagnosis rely on several measurement tools. These include clamp-on ammeters for spot checks, power quality analyzers for comprehensive analysis, and permanent monitoring systems for real-time tracking. Infrared thermography is used for thermal imbalance detection. Economic analysis shows that correction minimizes energy losses, restores normal equipment lifespan, and makes maintenance scheduled and predictable. Downtime becomes planned and minimal, and power quality improves, avoiding penalties. ROI is typically 6 to 24 months. Key takeaways emphasize that current imbalance is destructive and dangerous. Even small imbalances can reduce equipment life. Regular monitoring and load balancing are essential. The cost of correction is typically far less than the cost of operating with imbalance. This infographic summarizes the key takeaways, covering the destructive nature of imbalance, the impact of small imbalances, the importance of monitoring for early detection, the necessity of load balancing, and the benefit of correction over continued operation. The best practice is to implement a routine measurement program, quarterly or semi-annually, and immediately correct any imbalance exceeding 5%. For critical systems, consider permanent monitoring with automated alerts to maintain health and operational safety. Thank you for watching this video on the effects and management of unbalanced currents. Maintaining balance is crucial for system efficiency, longevity, and safety.